Hey everyone, I'm Chris Potts. I recently gave a talk called Assessing Skeptical Views of Interpretability Research at the Stanford AI Lab's faculty lunch. As you can imagine, with a group of faculty, this kind of drifted from talk into wide-ranging discussion, and I didn't get through my slides. So I want to do a full run through now to get it out of my system, but I'm also hoping this recording will stimulate discussion among Interp researchers about these more skeptical takes that people are having on our work. The talk itself is based around a blog post with the same title that I wrote this past summer, and that was in response to a meetup organized by Goodfire and Anthropic and focused on the present and future of interp methods in AI. So I'm going to stick broadly to the structure of that blog post, but my thinking has evolved on some key issues, and that means I can offer even hotter hot takes, especially on the key question of whether and how interp methods will lead to model improvements. To set the stage a little bit, I want to call out the show Severance. I hope people have checked it out. In case you missed it, in Severance, we're focused on a team of people that spend their entire professional lives staring at matrices of numbers on their computer screens. And because of the way these people are wired cognitively, some constellations of these numbers cause them to feel really big feelings. And when they feel these really big feelings, they can take an action that they assume is in some sense improving the overall situation. This is almost too on the nose as a description of interp research. I love the visuals, and as a result, I have adopted as a motto for my interp research, the work is mysterious and important. But back down to earth, back to reality. I want to give you a sense for the landscape of ideas for this talk. So I have interp at the center of the slide here, and the first thing I want to do is call out a contrast with what I'll call explainable AI. I'm not trying to legislate how we use these terms. I just need some label for the adjacent effort that is focused on informing everyday users about how AI systems make predictions. You could have in mind that we've defined an AI system that is making predictions about people's creditworthiness, and we owe those people an explanation of how the model makes its predictions. So this means we'll place a premium on explanations that can be understood by people with no technical training in AI, and that might lead us to favor simple models because those will be the ones that we can offer faithful, comprehensible explanations for. Interp, as I'm going to talk about it, differs from explainable AI in that sense along both dimensions. In Interp, we're typically focused on frontier models, which are not simple models in general. And the users we have in mind, the consumers of our explanations, are, we assume, people with a lot of technical training in AI. The other major factor that I want to call out here is that in the current moment, by far the largest and most prominent group of researchers doing interp is the one at Anthropic. And because of their prominence in the discourse and in scientific contributions, they exert a large influence over how people think about the field in general. And this is important because their perspective is very particular and not inevitable. The Anthropic take on interpretability is very closely connected with long-term questions of AI safety and existential risk. They are also very focused on kind of more speculative questions around what you might call AI consciousness, or things like whether LLMs will learn to motivatedly deceive us. And because of the semantic space that we're now in, you also get coloring from themes like effective altruism. I have no complaints about this overall perspective. I just want to point out that it's a very particular perspective on interpretability and not an inevitable one. And in particular, in the work that we're doing in my research group at Stanford, and I think the research on Interp at Stanford more generally, we're much more focused on themes of evaluation, which could be a stepping stone to improving long-term AI safety, but we might also have more near-term concerns in mind. And maybe the more important and interesting point of contrast is that in my group, we're very focused on model improvements. I think of myself as being on a mission to show that interp methods can lead to better architectures and more robust model artifacts. And this might actually be a point of contrast with Anthropic, where the focus of their research is on understanding the models that we've got, and in particular trying to make them safer, but not necessarily making them more capable or improving them in a general sense. But I wouldn't want to make too much of these contrasts because I think we have lots of shared interests. I just want to point out that my perspective is different from that very prominent Anthropic one. And the final thing I want to say here is that I'm confident that we're all united around the importance of deep scientific inquiry in this space. It is early days for interpretability, it is early days for AI, and the stakes are very high. It seems like a perfect moment to really invest in a deep understanding of how these models work. Before getting to the skeptical takes, I want to do a brief review of interpretability methods in general so that you have in mind the toolkit that I'm talking about when we think about the skeptical positions. So let me do that quickly. I'll start with attribution methods. This is probably the oldest class of Interp methods. Here I've got on the slide here a schematic picture of a stacked transformer-based large language model. That's by far the most prominent kind of frontier model that we encounter today. And we imagine that it has processed an input like the capital of Japan is, and it made a prediction Tokyo. And here and throughout the talk, the question is essentially, how did it make that prediction? And with attribution methods, especially the oldest of them, we're typically focused on input attributions, understanding how input features affect the behavior of the model. You could have in mind here things like feature ablations, permutation feature importance, and Shapley values. A more recent class of attribution methods is exemplified by the LIME model. With LIME, we have an auxiliary model, a simpler model that we're going to use as a proxy for understanding our target model. Here I've chosen a decision tree for my LIME model, but it can be any interpretable ML model. And the idea is that we'll train the LIME model to conform to the behavior of our target model, not only for our chosen input, but also for various permutations of that input. We're trying to align the behavior of these two models so that we can use the LIME model and its various feature values as a proxy for understanding the input features of our target model. Methods like LIME don't give you an understanding of how the internals work, but rather just how inputs affect outputs. In the deep learning era, many attribution methods are what you could call gradient-based attribution methods. So here again, we have the model process some input, but now we're going to take gradients with respect to some dimension of its output predictions and track those back through to the neuron that we want to do an attribution for. And the best of these methods will give us a sense for the magnitude of the contribution of that neuron to the input-output behavior for this example. Many of these methods can do attributions not just to the inputs, but anywhere in the model so that they can be used to analyze the internals. And also the best of these methods are giving you a sense for like an estimate of the individual causal effect of the neuron on the input-output behavior of the model. In my group, we've made very productive use of integrated gradients, for example, as a very powerful general attribution method. A more recent class of methods in interpretability are the probes. These really came to prominence around 2018 in connection with the BERT model. I remember it being incredibly eye-opening at the time to see via probes that models were learning to encode lots of very rich modular internal structure as a side effect of how they were being trained. To give you a sense for how probes work, I again have a schematic LLM on the slide here. And I could ask, for example, the question, how much part of speech information is encoded in this particular layer in the model? And to answer that question, I would train a supervised probe against some part of speech data set. And I would use the performance of that probe as an estimate of the amount of part of speech information in that layer. You could also fit more focus probes, for example, just on a single representation trying to understand via a supervised learning problem how much information about capital cities is encoded at that point in the model. And we also have unsupervised probes, and by far the most prominent class of unsupervised probes are the sparse autoencoders. The goal behind sparse autoencoders is to take the typically very dense representations inside our models and unpack them into very large sparse representations with the hope that the individual dimensions of that sparse representation will be themselves interpretable. The oldest work on sparse autoencoders in this sense that I know about is Aurora et al. 2018, Linear Algebraic Structure of Word Senses with Applications to Polysemy. But these sparse autoencoders really came to prominence via work that Anthropic did a few years later. And by now, people at Anthropic and people elsewhere in the field have explored many variants of SAEs, trying to do this kind of very free-form, unsupervised feature discovery of the things that are encoded latently in the internal representations of our best models. The third class of methods that I want to call out here are intervention-based methods. These are very general, and I think they're coming to be core to the toolkit in interpretability. And in fact, the previous approaches, probes and attribution methods, can be combined with interventions. The core idea behind an intervention is that I'm going to do something to the model to put it into a counterfactual state to understand something about its causal structure. So for example, I have my model process the capital of Japan is, but now I might just wipe out part of the network itself by zeroing out the values or replacing them with the mean value over some sample from my population of examples. And then I just see what effect that has on the output. If it has no effect, maybe I've learned that the model is in some sense conceptually sparser than I thought it was, but maybe I learned that that part of the model was really causally impactful. Another kind of intervention is a perturbation intervention. This would be where I go into one of the representations and just randomly change its values a little bit to see what that does to the input-output behavior of the model. This could be a kind of robustness check, but I also might, of course, train the model against those perturbed representations to make it more robust. And here, in mentioning this kind of intervention, you can see that, for example, many input attribution methods, including LIME, can be thought of as intervention-based methods. The kind of intervention that we've been most focused on in my group is what we call interchange interventions. They're also sometimes called activation patches. This is an idea that has been discovered and rediscovered a few times in the field, and I think that stems from the fact that it's a very natural consequence of thinking about neural networks as causal models. So let me give you a sense for how an intervention works by way of a simple example. So I've got on the slide here a large language model, and I have it process this mathematical expression, and it makes a correct prediction. And I'm choosing these mathematical expressions so that we can have in mind the kind of causal model that's behind what we want from the network in this case in terms of its predictions. And here we assume that the model is doing well. It makes a correct prediction about that input. Now I take the same model and have it process a different input. And again, let's assume that it makes a correct prediction. And we want to understand why the model is so good at this hard problem. To do that, I'm going to pose a first hypothesis. And my hypothesis is that the representation that I've circled here is a modular encoding of the sum of those two input numbers. It's going to be part of my explanation for why the model is so good at this particular task. To test that hypothesis of modular encoding, I'm going to take the corresponding representation in the source example on the right and literally put it in the corresponding place in the base example on the left. And if that replacement intervention causes the model to change its prediction to 6, then I have one piece of evidence that my hypothesis was right, that that representation is a modular encoding of the sum of those two numbers. And if I can repeat that experiment successfully for many, many inputs, I will be approaching a proof that indeed that representation modularly encodes the sum of those two numbers. And I could continue to do this intervention-based work and piece together what I hope would be a full understanding of the true causal structure of the underlying network. Now, one technical point here before I move on. Typically, in my group, we have not done that literal replacement intervention, but rather something more surgical that we call a distributed interchange intervention. And the idea here is not to do a complete replacement of the base value with the source value, but rather find a direction in feature space and do a replacement just of that particular feature. And we have posed that typically as a supervised learning problem in which we learn to find the feature and then do a soft intervention on the base that should preserve orthogonal orthogonal dimensions in the base while finding the feature and doing the replacement of the feature that we care about. This is a more surgical intervention because obviously each one of these representations encodes lots of information beyond the feature that's of interest for the particular experiment. The final thing I want to say here is that this has been a very exciting space to operate in terms of building up the theoretical foundations. Earlier this year, a large group of us, led by Atticus Geiger and Thomas Eichardt, published a very large theoretical paper that is focused really on understanding what class of interventions will be productive as interpretability methods. Obviously, if I can do any intervention that I want on a network, I could even create an entirely new network, and that doesn't seem like it would count as interpreting the original target model. but what class of interventions will get it right in terms of allowing freeform discovery of interpretable features while also being faithful to the underlying model. So that's a question that we make some progress on in this large theoretical overview, and it's been the subject of a lot of interesting debate across a number of different papers where people have claimed that a method was too expressive. We have tried in a few cases to respond. I regard this as part of an ongoing discourse that's going to help the community come to an understanding of the most productive class of interventions that will allow us to really discover it in as unbiased a way as possible how models are learning to encode information. All right, with that background in place, let me move to these skeptical positions. And this comes more or less from the blog post, and I'll just review them quickly and then we'll dive a bit deeper. Skeptical position 1, interpretability cannot be achieved. Number 2, interpretability is merely analysis. Analysis is overrated. Interpretability is not leading to improvements. And finally, interpretability is not helping with AI safety. Let me give you my quick responses. I think the first one is a call to action. For the second one, I would like to just ignore it. I feel a little bit like people are trolling me. I'm trying to ignore this, but I can't help but feel invested, so I will review that argument. And then the most interesting ones, in my view, are the ones that are given in red there. For both 3 and 4, I think those are really interesting, and this does mark an evolution in my own thinking about these issues. And for the question about interpretability helping with AI safety, I want to say it's true that it hasn't yet helped, but the situation there is complicated, and it has both scientific dimensions and probably social and cultural ones. So I'd like to review that in some detail. But let me start with the easy ones. First, interpretability cannot be achieved. I think when people offer this skeptical take, what they have in mind is a kind of framework like this. Along the x-axis, I have model complexity increasing from left to right. And along the y-axis, I have explanation complexity increasing from bottom to top. And the concern, I think, is that we need the field to achieve something like this blue line, where at a certain point, even as models are getting more complicated, our explanations are not getting more complicated in turn. And the concern, though, is that inevitably somehow the explanations will end up at least as complicated as the models. And of course, if they do that, they have very little utility because it's very unlikely that we as humans will be able to understand them. So I think the claim that there's a kind of lawful connection here that will make explanations grow at least as rapidly as model complexity is behind this skeptical take here. In response, I would point out first, everything along the x-axis here, all these models are designed by us. At least for now, before we get to the day when AIs are designing their own AIs, these are all human-created artifacts. And that should be a huge advantage. And just think about my colleagues in neighboring scientific fields studying the solar system or the human brain or weather patterns. Those are much more complicated, clearly, than the models that we're talking about. And those scientists seem undissuaded. They are persevering and trying to find deep causal theories of their domains, explanatory theories that will lead to progress. And I would just say, I think we should be at least as ambitious as they are in our goals here. So my overall verdict is, this is a call to action. We will achieve the right kind of explanation for humans. This second skeptical take, as I said, I kind of feel like I'm being trolled here, but I do feel like I have to dive into it. So here's how this goes. For example, we published a paper called Causal Abstractions of Neural Networks, and that's where we really developed the theory of interchange interventions as an analysis tool. And then subsequently, we published a series of papers that used interchange interventions to improve models via a mechanism that we call interchange intervention training, which essentially imbues models with internal structure by training against the counterfactual model states that you get from interchange interventions, but also allows models to learn in a standard data-driven way. And that's exciting because you end up with models that are more performant and also embed a lot of interpretable structure. I found that exciting, and obviously those training methods were built directly on our insight about interchange interventions. So it's frustrating to me that very often people's response is, the first thing you did is interpretability, but everything else was just a model training effort. If people feel they have to say this, I guess I can be accepting of it. But I do just want to emphasize that all of those improvements were on the back of an interpretability result. And I have to offer just one more example here. So for interchange interventions in the distributed fashion, I pointed out we do these kind of things and we can have lots of different intervention functions. I pointed out the distributed one, but we could also have the vanilla intervention. And at this point, you can see there could be lots of ways to think about parameterizing these interventions and training them that could lead us to lots of new kinds of insights. We were on that journey, and that led us to discover that we could do a kind of self-intervention that we call REFT that would function as an alternative to standard parameter efficient fine-tuning. That would be a very general method for improving methods using very efficient fine-tuning techniques. And in this case, it's a minor variant of the distributed interchange intervention where instead of having a source example, we just have a simple learned linear model defined on the base. A self-intervention. And I think this is very effective. And the reason that it's effective is because via interpretability, we learned that there is a lot of modular, interesting structure in the representations, making them a great target for fine-tuning. But again, a very common response has been, the first thing you did is interpretability, but the ref thing, that's not interpretability. Again, I find that frustrating because of how direct link was in our own research, but maybe the right response here to all of this is to just say, we should ignore this criticism and just get on with the work. All right, let's move to a more serious class of skeptical takes. These are the ones where my thinking has been evolving somewhat over the past months. And I'll start with analysis is overrated. And this can come in a few flavors. Let me start with the simplest one. The response is just AI is an engineering field. We just do what works. I actually think this is reasonable. And the only thing I would point out here is that inevitably, in science and in engineering, when people discover causal theories of the domain, it is always generative. It always leads to big breakthroughs. And so while it's fine to just operate in a mode of doing what works, in the back of your mind, you should be hoping that some people are trying to find those deep causal theories because of the leaps forward that it will enable. The second flavor of the skeptical take is one I'm a bit more receptive to. Here we say AI is young. We're in the messy experimental phase. I want to circle back to this because I think there is something interesting about this. And I hear in this a kind of skepticism about the very focused and rigorous work that we typically get in interpretability research right now versus the kind of messy discovery process that you might undergo if you're just trying to figure out what works. And that leads me to what I think is the most interesting version of the skeptical take. This one says, progress has been incredible in AI because of deep analysis. So this is not saying analysis is overrated, but what it is saying is that analysis of the interpretability sort is overrated. Progress has been incredible because of deep analysis, but not the sort of analysis that you see in the toolkit that I offered at the start of this talk. And that, I think, is a very interesting kind of criticism to think about. And for an illustration of why I think it has some teeth, let's consider the transformer. The transformer was introduced in 2017, and it is still the fundamental unit of computation for almost all frontier models today. We talk about it like it's the same thing from 2017, but in fact, it is radically different. Essentially, every aspect of the transformer has been revamped by the time of 2025. The positional encodings are different. The attention mechanism has been completely rewired. The multi-layer perceptrons that do so much of the computation for the transformer have also been completely redefined. And even the kind of glue between these parts of the transformer, as exemplified here by the layer norms, that's also been completely rethought and redesigned. Basically, the only thing that survives from 2017 is the attention plus MLP combination. Everything else is different today about the transformer. And I claim for you that the reason we've seen so much progress on this is because of very deep analysis and understanding. The people behind these innovations have a very deep understanding of how the transformer works and how it processes information. And they have done a lot of analysis to achieve that level of insight. But the concern that you could have is that it's not the kind of very rigorous, structured analysis that you get from interpretability right now. And for a quotation you could have in mind here, like this famous one from Noam Shazir, he's talking about one of his innovations to the multi-layer perceptrons, and he says, "We offer no explanation as to why these architectures seem to work. We attribute their success, as all else, to divine benevolence." I think that's a bit glib, but I kind of know what he means in the sense that he can't fully trace the causal path from his innovation to the improvements that he sees. But I also want to say that I think in truth, this is based on a very deep understanding that he has about how the overall architecture is operating. But again, the concern that I feel is that that is not a set of insights that derives directly from the toolkit that I showed you at the start of this talk. And that could give us some pause. I've been thinking a lot about this, and part of that is because I read a fascinating book by Nicole Rust called Elusive Cures. This was recommended to me by my colleague Mike Frank in Stanford Psychology. I don't think he was trying to communicate anything to me in particular about my research on interpretability, but it did really hit home for me, and here's why. This is a quotation from the book. Rust says, "Here, then, is an answer to the question of how brain research works that is quite distinct from the bench-to-bedside narrative we started with." Right? The bench-to-bedside narrative is this idea in neuroscience that fundamental work we do in the laboratory will lead directly to better treatments for patients. And my variant of that is like Interp to frontier LM, where I'm hoping that our work on the methods for interpretability lead directly to improvements for our biggest and best and most important models. That is my version of the bench-to-bedside narrative. And Rust is expressing skepticism about that narrative in neuroscience. She continues, "To date, the creation of new therapies has involved all manner of serendipity and shortcuts that circumvented understanding." And here I can't help but think back to Noam Shazir's comment about divine benevolence. It's not that the big breakthroughs in understanding haven't contributed to new treatments in any way. It's just that this prototypical description turns out to be not much of a prototype at all. It's been much more of an aspiration than a realization. And I think that is a fair assessment of, for example, my story about the transformer. I would love it if MechInterp research had been behind every single one of those innovations, but I have to be accepting of the fact that by and large, it was a more free-form, intuition-based analysis that led to those improvements. And I do just want to say here that I'm still optimistic, and I am hoping that I can help build a future in which interpretability plays much more of a central role in achieving exactly those kind of insights for the next generation of architectures. But I think we are not there yet. However, I don't want to go overboard. For, in particular, the skeptical take, interpretability is not leading to improvements, I want to just say, I think this is false. And here is a bunch of examples on the slide here. To keep this constrained and focused, I have limited attention specifically to results that use the toolkit that I mentioned at the start of this talk so that this doesn't generalize to any kind of free form analysis. Already, I think this is an impressive list of results. And the one interesting qualification that I want to offer to this list is that I think it could be much longer, except for the fact that many people in the field, as I said at the start of the talk, are not really focused on model improvements. And here, for example, again, I could call out Anthropic. They're doing tons of research, but much of it is focused on questions that are not about model improvements. This is a list of their recent blog posts, and I would say the persona vectors one is focused on improvements to models in the form of steering. But by and large, what I see in this list is contributions to the fundamental science, that could be like the circuits work there. And in addition, kind of more speculative, future-oriented work around questions of deception and motivation inside these models. So that's just a different set of questions, and what it means is since the energy is being focused in that direction, it is not being focused on model improvements, and that might lead overall to us kind of understating the potential of Interp to help with the question of model improvements. I am not trying to legislate anyone's research agenda or say that model improvements are the only thing the field should be focused on, but rather just to point out that I think counterfactually, the potential is even greater than what we've seen realized in the literature so far. All right, so kind of summarizing these two positions here. For analysis is overrated, I want to say no. Analysis is vital, and it is underrated in AI. but it could be a mistake to fixate on a specific toolkit instead of doing the kind of more free-form, intuition-based analysis that has so far been an engine of incredible progress. Interpretability is not leading to improvements. I think this is just false. I showed you the slide of results, but we do need more examples. And we might not get them at as fast a rate as I would like in virtue of the fact that the Interp community is currently focused in large part on other issues. Final skeptical take here. Interpretability is not helping with AI safety. This is a bit of a twist. I want to say that is true so far. But the question is, why is that true? Now, I think the first reasonable response you could give is that the problems of AI safety are very difficult and the field of Interp is very young. And so it's simply too much to ask that already at this point in history, we would have helped with a problem in AI safety. I think that is entirely reasonable, but I still have a concern. And the concern is embodied in this question. Is the community positioning itself to help in the future? I fear not. I fear that in focusing on far-off scenarios related to AI safety, the community risks becoming permanently disconnected from real present and future problems. My argument could go like this. We have present-day problems, and they're going to continue along a certain trajectory. The best path for success in terms of helping with the future problems would be to partner with the people solving the problems today and help them for that entire time. That is the best chance that in the future, when the big problems arise, you'll be there with the right toolkit and the right methods and the right insights to help. If instead the community decides to travel a different path from the ongoing path of AI safety, it might end up in a very different place. And I think that greatly reduces the probability that when the big problems arise, they will be there to help. It might be that they've developed methods, tools, and insights that just don't have anything to do with the problems that actually arose. And to prevent that, I would suggest much closer partnership between Interp researchers and the people at the front lines of the problems in AI safety today. Here's a quick example. So earlier this year, we saw a big announcement about how a GPT-4o had a problem with sycophancy. All large language models seem to have a problem with sycophancy, but 4o arguably had the problem in a very deep way. Now, the problem was identified. People found some subset of the underlying causal factors, and they were able to take some steps toward mitigating the problem. There's by no means a solution here, but there was real progress, and I think that stems from the fact that as a community of researchers in AI, we do have deep understandings about how these models work, and that's how we were able to so quickly move to begin to address the problem of sycophancy. My concern is that as far as I know, Interp researchers played no role in that process. They didn't help with identifying the problem or finding the causal factors or helping with a solution. And that is concerning to me. And I have an even deeper concern that the response from the Interp community was kind of like, well, that's a low-level kind of problem, not the big problem that we're worried about, so we can safely ignore it. I think the response should be the opposite. Sycophancy probably is a safety problem, and if not, it is certainly safety adjacent. It is going to be a complicated problem that is probably going to grow over time. That makes it a juicy and difficult problem for Interp researchers to try to make progress on. If not just so that we can help out with the ongoing problem, but also so that we have good skills and methods and so forth in place for when the future problem actually arises. This is the best way to ensure that we've got what we need in that situation. So I see wins all around here for Interp research if they just express a willingness to participate directly in helping with these ongoing concerns. And I think I can close on an optimistic note here because what I sense happening is that Interp groups are trending in that direction. For example, this is kind of anecdotal, but I have noticed that Neil Nanda, who runs an influential and important research group at Google DeepMind, has shifted his own narrative around interpretability somewhat more toward practical questions. For example, in this podcast interview recently, he said, "I have become a big convert to probes. They are a really simple, really boring technique that actually work." Now, I don't know anything about the nature of Neil's work at Google DeepMind, but I could speculate that what they've seen there is that probes are a really good lightweight, effective method for catching problems with models before any actual generation happens with them. They're lightweight, they're efficient, as he says, they can be highly customized, and they can really help out in those everyday safety scenarios. And I love that because I think this is exactly the kind of work that you would do if you wanted to be on the path toward helping not just with the current problems, but also with the big problems of the future. And I think even Anthropic might be trending toward my overall position here. I was delighted to see in the Claude Sonnet 4.5 system card that there is a very deep and interesting interpretability analysis that is paired with their alignment analysis and focused on the issue of evaluation awareness. And this is just the observation that models seem to latently learn to classify inputs to them as either real examples or test examples. And then the concerning behavior is that when they're given test examples, they act more safe than they do when they're given real examples, which is concerning for us when we want to estimate safety for these models overall. And not only that, but in this little analysis in the system card, they also take steps, kind of speculative, but still promising, toward mitigating the problem by doing SAE-based interventions to reduce the amount of evaluation awareness, to get a clearer picture of the actual safety level for the model. I love that. It suggests so many things about how we could help with this ongoing problem that I think, again, is a glimpse of the kind of problem that we're going to face increasingly in the future. So that was all just wonderful to see. So to wrap up, let me close in a kind of amusing place. This is just a summary of my skeptical positions. And then here is a sweatshirt that my student Aryaman Aurora wore at NeurIPS in 2024. One side says interpretability is useless. The other side says interpretability is useful, and he got people to sign based on which of those two positions they endorsed. In 2024, we got more signatures on the useful side, which is great. And I want to point out here that Neil Nanda did not, in fact, sign on the useless side. That was one of his students playing a prank on him, and Aryaman crossed out his name, just for the record. And my expectation is that going forward, we can see lots more people wanting to side on the useful side. But that is going to have to come from us making contributions that help people see exactly how interpretability is useful. So we need to kind of be the change that we want to see in the world and ensure that models improve as a result of the work that we're doing in interpretability. I am very optimistic about that project because of the number of super exciting, very smart people working on these problems. And I would just invite you all to be part of this exciting future. Thank you.